So on this podcast, we're going to discuss how structure can affect the properties of acids and bases. How does this structure dictate whether an acid will be a strong acid or a weak acid? And it's about how it keeps that H attached to itself or not. So any molecule with an H on it can potentially be an acid. It depends what that H is attached to that will help determine that. There's a couple forms of acids that I have listed here. We're not going to discuss all of them. Actually, discussing most of them except for one. The first one is hydrochloric acids. Hydro means hydrogen. Helic means halogens. So basically, any acids where it's forming with a halogen. So HCl, HBr, HI, HF is another example of a hydrochloric acid. An oxy acid is an acid where the H is attached to an O. So let me give the first one here, perchloric acid. That H is attached to an O, which in turn is attached to a Cl, which we call a central atom. And that Cl is attached to two O's. So we call this an oxy acid because of the H that's attached to that O right there. You'll see this in all oxy acids like this, and then this will be attached to a central atom, ClBri, basically a different element. I'm just listing this here, carboxylic acid. I'm not going to discuss this in this vodcast, but I just wanted to throw that out there that there's another type called carboxylic acids that will not be discussed for this vodcast. But I will discuss hydrated metals. And so hydrated metals is when you have aluminum that's a highly charged metal ion, +3 or higher, and it's going to have 6 waters attached to it. So we're going to discuss basically these three right here, this one, and this one in this vodcast. So there are two factors you have to take into consideration when talking about all these acids. One is the strength of the acid. The strength of the bond between the H and the X. If the bond between the H and the X is very strong, that means that this H is not coming off, and that would be considered a weak acid. It makes sense. X is very strong, H is not leaving. If the H is very weak, if the X is very weak, that means that the H comes off very easily, and that means it's going to be a strong acid. Don't forget, all strong acids basically dissociate in solution. Another factor we take into consideration is polarity, basically how polar a bond is. So just as a refresher course, if I have a fluorine molecule here, which is just basically two F's, and so this is what fluorine looks like, and it's got these electrons around it. There really is no uneven distribution of electrons. There is actually a symmetrical distributed of electrons around it, evenly distributed among each element. So this is what we call a nonpolar compound. There's really no uneven distribution of electrons. If you take the opposite end of the spectrum, I guess you can say, hydrogen with fluorine, it's got a lot of electrons on one side and 0 on the other. So there's a very uneven distribution of electrons on one side, and we would consider this is what's called polar. So the more polar the bond, the higher the chance that the H will come off whatever element it's attached to, compared to a very less polar bond. The H will probably not come off at all if the polarity is slim to none. So, and it has to do with this distribution of electrons. Is it symmetric or non-symmetric? Remember, polarity is basically an uneven, and non-polar means that there's an even distribution of electrons. So the first one we're going to look is hydrochloric acids. And basically the strength of the HX bond determines the biggest factor that it determines how strong or weak the acid is. Now, the bond between H and F is a very strong bond. Do not forget that fluorine only has 2 layers of electrons. It is located in the second row. Chlorine's in the third row, bromine's in the fourth row, and hydrogen's in the fifth row. So when we get to iodine, it's got 5 layers of electrons from the quantum model compared to HF. That F is keeping that H on there very, very tight, and that's why you have such a very strong bond strength. This is how much energy it would take to break that bond, 568.2 kilojoules per mole. So it is considered a weak acid because the bond strength is very, very strong, because the F is very good at keeping that H attack close to it. And again, it has to do with how close it is to the nucleus. Once you start getting to the third, fourth, and fifth layer in halogens, the bond strength decreases. And here, the H off the I comes out very, very easily because it's a very weak bond between the two. And in a nutshell, all three of those are considered strong acids. And that's one of the things you have to memorize. HCl, HBr, and HI are strong acids. Now you can see why. It is because of the structure of the H and the Cl is what determines that big factor. Okay, the next type of acids are called oxy acids, and then we're going to use basically the chloric acid and its derivatives as an example. So the more oxygen hooked to the central atom, the more acidic the hydrogen. So I'll go in the structure and it'll make more obvious in the next few slides. But we know that we had to memorize that HClO4 and HClO3 are strong acids. These two are considered weak. Of the entire group, HCl will be the strongest acid, and we'll show by structure why that's the case. Remember that the H is attached to the oxygen atom, and the oxygens are electronegative. So that means it has a lot of electrons around the oxygens, and basically it's going to cause this polarity in the molecule, and one side will be a lot more electrons than the other side. And it basically pulls the electrons away from hydrogen. So the best way to really look at it is by structure. We're going to take the first derivative here and kind of take a look at it and what makes it a weak acid. So here we have HOCl, and there are electrons around this chlorine, so it's electronegative. But this is considered a weak acid because there's not really that much of an uneven distribution of electron here. This oxygen is what's basically competing. If there's a lot of free electrons on the left side and not a lot on the right, the H is going to come off. So since O only has this one Cl, it can keep that H on here very easily. So there's not a lot of electron density on the left side than there is on the right. Okay, we look at its derivative. Now that chlorine has an O attached to it, and again we got a lot more electrons on this left side. And when I say left side, I'm talking to the left of this guy right here. So basically on the left side of this atom, there's a lot more electron density over here. And because there's a lot more electron density, this O is having a harder time keeping that H attached to it because of this very uneven distribution of electrons in the molecule. It's still considered a weak acid though. It still keeps that H pretty well attached, but it's still a stronger acid than the previous one. Okay, next we're going to look at now we know that HClO3 is a strong acid, and you can see why. Basically there's a big electron density right here, all on this side. Humongous electron density on the left side. So this H comes off very easily. This O cannot keep that H attached to it because of the electron density on the left side of the molecule. This is definitely a stronger acid than the previous two. And then you go to the last one, perchloric acid, which the electron density is just too great on the left side of this O, and that H just pops right off very easily, and that's what makes HClO the strongest acid in the group. It's because of this humongous electron density on the left side. A very, very polar molecule compared to its derivatives. So that kind of explains how oxy acids are strong versus weak. It is basically how polar the molecule is. The more there's electron on one side, the more it's going to lose that H. The last one we're going to discuss is hydrated metals. And basically hydrated metals is basically pulling the electrons all close to the center of the metal. So as a reminder, do not forget When we talk about hydrated metals, aluminum obviously is the most common one. It's going to have that 6 waters attached to it and still have a +3 charge. One of the H's off the water is basically going to break off, and that's why a hydrated metal is basically acidic in solution because of that. So highly charged metal ions pull the electrons of surrounding water molecules towards them, and it's going to be 6 water molecules because of the structure. And it basically, one of the H's off one of the waters will come off very easily because the electron density is all being pulled towards the center of the molecule, and one H will pop off to make an acidic solution. So just as a recap, to balance this, and as good practice, do not forget how to write a hydrated metal ion. You have 6 of these with a +3 charge. Eventually you're going to have aluminum, OH ion. It's 5 waters now because one of the waters has lost its H, with a +2 charge, and then it's going to have a +H. So hopefully this should be familiar with reactions of basically a hydrated metal, any metal with a +3 charge or higher. And because the electron density is being pulled to the center of the metal, it makes for the H's to come out very easily. Alright, there you go. So I hope that helps with the structure and help differentiate between weak and strong acids based off of structure.